if we're okay with that, let's just compare to how we would tackle a similar projectiles question just in terms of I and j vectors. So we have here, I'd say, a very similar diagram. We're again starting at a point A that's above the ground, and it's going to make this arc to hit the ground from over here, and we have an angle of alpha. But this time, rather than having a known speed, we are just given the velocity in terms of vectors. We have pi plus qj. Now, because this is already in vector form, we don't have to worry initially about doing any kind of sine or cos. We can just say immediately that this on the base of the triangle here is going to be a velocity of p, and vertically up here that will be a velocity of q. Now then the ball takes 3 seconds to reach B, so ball being projected from A here. Find P, show that Q equals 14.4, find the initial speed, find the exact value of tan alpha, find the length of time spent above 4 meters, and then state a physical factor that would make this more realistic. So we've got a lot of elements that we're going to be dealing with here. I'll obviously just start from the top. So if we're going to find P, well, P is obviously in the horizontal direction. So as before, for the horizontal, we can just deal with a speed equals distance over time, or velocity, I guess, more so in this case. Either way, so it equals the distance over time, which in our case, the horizontal distance is the 57.6. And that will be over time. We're told it takes 3 seconds to get there. Therefore, we can say that the velocity of P must be 19.2 meters per second here. Now, to then show that Q is 14.4, we're going to work in some similar principle, although of course, because it's in the vertical, we're going to have to use suvat. So, we know that by the time it reaches B, vertically, it will have had a displacement of minus 0.9, because it will have dropped this distance of 0.9 here. Now your U is going to be that Q. V, we don't know what it's going to be, but A is going to be minus 9.8 for gravity, and then T, again, we know is 3 when it hits the ground. So we're going to be again using S equals UT plus half AT squared, but we're going to have to rearrange. The arrangement we're going to be using is going to be U equals S minus a half AT squared all over T. So plugging in the values that we have, that gives us Q equals minus 0.9, well, minus a half A, well, minus becomes a plus, so plus 4.9, then that's going to be 3 squared here for your time, over, again, that time of 3. So this gives us a value of Q of, as you may expect, 14.4 meters per second of what we had to show. Now when it then says the initial speed, again speed is the resultant, it is the magnitude, so we're going to have to be working with the essentially Pythagoras. This will therefore be the square root of the 19.2 squared from over here, and then that 14.4 we just proved squared. And if you work that out, that gets your initial speed equaling 24 meters per second. Now, as for the exact value of tan alpha, because we don't need alpha, we can just go straight into say, well, tan alpha will just be the opposite over the adjacent. So that will be 14.4 over the 19.2, which you actually can find is the same as 3/4, which is also what you would expect from what we had above in those previous examples, where so like sine alpha is 4/5 and so forth. Sorry, 3/5. Now, to then find the length of time spent above 4 meters, again, because we're looking at how high it is, not how far it's gone left or right, we're just going to be focusing on the vertical once more. So, if we're looking at being 4 meters above the ground, and yet we're already starting 0.9 meters high, we're just looking for a vertical displacement of 3.1. Now our U, the initial vertical velocity, again just the vertical, we already know is going to be 14.4. We don't know what the V is going to be, but A will be minus 9.8 because we're decelerating downwards under gravity, and we're trying to find time. So plugging this into an s equals ut plus half at again, you end up with 3.1 equals 14.4 t, and then minus 4.9 t squared. Move this all onto the same side, 4.9 t squared minus 14.4 t plus 3.1 equals 0. This you can put into the quadratic formula, and you'll find that t is going to either be 2.4 or 0.2. Which makes sense because it's an arc like this. If we were to say, I don't know, maybe the 4 meters is somewhere here, right? It first of all goes through this upwards, but then also crosses this threshold back downwards as well. There's going to be 2 points where it's at 4 meters. So the time for which it is above 4 meters is going to be the difference between these two times, which is going to be 2.5 seconds. And lastly, if we're just saying, well, what's a physical factor that makes it more realistic? As you may realize already, whenever we do these models, we set in some kind of caveats just to make things easier for ourselves. If this was happening in real life, there'd be a few more things we need to consider, such as air resistance. If there was air resistance, then the acceleration would be different because there'd be other forces pushing back on the moving object. Or you could say that the ball is not a particle, that it would have a greater mass. Well, its mass would not be focused on one single point, it would be spread over a larger volume, had different surface areas, and so forth. So as again, as you see, it's very similar to what we had before, it's just we're now considering things in terms of I and j, right? Which means we don't necessarily have to worry about doing the whole sine and cos side of things, so we can just read off the coefficients of those vectors. So with that in mind, just to see how we get along again with another one. So the particle P is projected from the ground with a velocity of k lots of 3i plus 4j meters per second. Now, given that the greatest height is 24 meters, find k and the horizontal distance travelled. Once again, just pause the video to have a go for yourself, and then press play again when you're ready to compare. Okay, so this time we indeed aren't starting from an elevated height, we're starting from the ground, so we're just going to have a flat surface here, and then from some starting position here, P is going to be projected with that initial velocity, and then it would just go up and then back down again. We know that this initial velocity is going to be the k lots of 3i plus 4j, and because that is in terms of I and j, we can just already split that into a vertical and horizontal components, where this horizontal here is going to be 3k here, because when it's times out, and the vertical will be 4k. Now we also know that the greatest height is going to be 24, so that's meant to be in the middle of the arc there. So with that in mind, find out what k is going to be. Because we may wish to work in the vertical direction this time, we're going to use suvat, because the reason why we use vertical is we have a vertical height rather than a horizontal distance. So s is going to end up being 24 because we rise that high. U is going to be that 4k in the vertical. V, we can say, is going to be 0, because if it's the greatest height, it must have come to a vertical stop there. It's still moving horizontally, it still has a horizontal velocity, but vertically it's come to a stop. And then the acceleration is going to be the minus 9.8. So we can use v squared equals u squared plus 2as, or in the rearrangement, u equals the square root of v squared minus 2as, which if we just plug in our values, we're going to have 4k equals the square root of, well, 0 squared is just going to be 0, so let's just focus on the minus 2as. So minus 2 times your number here, so minus 2 times minus 9.8 times by the 24. So that gets you 4k being 28 root 15 over 5. And I'm going to suggest that you keep it in fraction form, just because otherwise you're going to have to decide where you're going to round the decimal, and by rounding you're not making it exact. And if this is 4k, then k will in turn be 7 root 15 over 5. Okay, well now that we have k, now we can go about working out the horizontal distance, because now we can work out what the horizontal speed is going to be, or the horizontal velocity. Once again, because we are in the horizontal, we're just going to be using speed equals distance time over time. We want the distance, speed times time. Oh, we don't know what the time is. We don't know how long it takes to land again. We still actually have to think in the vertical. So we need to work out what time it will take to land. However, actually, while at this stage, we could say set the vertical displacement to 0, because it'd be landing on the same plane it left. So even though it's travelled to the right, that's not a vertical direction, that's not a vertical distance. Vertically, the displacement would be 0. That would involve using u, and honestly, considering what fraction we have for u, it may be easier if we try to use s, v, a, and t instead. Yet we don't know the v when it hits the ground. The only v we know is when it's at the maximum height. So we'll have to use that. We'll only get the time to go halfway. But the key is there that it's halfway. That because there's no air resistance, these arcs are symmetrical. So the time it takes to get from the ground to the top will equal the time it takes to get from the top back down to the ground. So if we can just find the time from this suvat, we can then just double it. So s equals now vt minus half at squared. Let's see the variant of that suvat. So the 24 equals, well, vt, doesn't matter, we don't know what t is because v is 0. And then minus half at squared, or minus minus becomes a plus, so that becomes 4.9 t squared. Therefore, if you just obviously divide by the 4.9 and then square root, you end up with t being 4 root 15 over 7. Now, therefore, the time in total, which is going to be double that, we're going to get as 8 root 15 over 7. Now that we have the total time it takes to go from start to finish, now we have enough information to do the speed equals distance times time we were mentioning before. So distance is going to be speed times time. The horizontal velocity, that speed, that's going to be 3 times this fraction here. So that's going to end up being 21 root 15 over 5. Now times that by this time of the 8 root 15 over 7, and this actually gets you a distance of just 72 meters in the horizontal. Now, while it's not guaranteed that getting a whole number is your answer, it definitely means it's right. The fact that we've had fractions like these coming out to such a round value is probably a good indicator that we were on the right lines.